Good. So, there we go. So, hello. The topic today is t-statistics. Last time I think I said generalized least squares, but it doesn't really make sense to do generalized least squares if we haven't talked about t-statistics first, because then the motivation for doing some other kind of estimation, namely not maximum likelihood or unbiased sample mean and sample variance estimation, is not really clear. So we first have to talk about t-statistics.
Can I ask a question to the audience?
Sure. Let's just briefly start where we are, and then we do questions. So we are in the process of estimating the GLM. So that's what we've done last time, where we introduced the beta head estimator and the variance estimator. And I think last time we had in the denominator only n-1. Maybe I mentioned that using restricted maximum likelihood, you can improve this estimator, the maximum likelihood estimator, where then in the denominator you have n-p. And today is basically to use these estimates and the distribution of the errors to arrive at the notion of t-statistics. Yeah, so that's where we start. So questions about last time?
I still have the same question as last time. Because I was wondering, because I also used it in my bachelor thesis, when we have the errors we just know because we're measuring. Because in the MRI signal we're measuring current or voltage or something like that, right?
We're measuring the MR signal, and we have gray values that we then analyze over time.
But I mean the MR signal is kind of a current.
Yeah, but in the end, everything, it's not really about being a current, but it's being after the reconstruction of the images. So of course the raw MR signal is some frequency power, and this is then reconstructed into the images, and what we have as the MR signal of each voxel, that's the gray level value of this voxel over time.
Right, but what I mean is, whenever we measure something in an experiment, we don't know, the last digit is always kind of uncertain because we cannot measure it like really exactly, right?
Yeah.
So, okay, probably this error is like quite small in the MR signal, but just in theory, if this would be bigger because our devices are not as good, we should take this into place, right? Like put it in our estimation, because now we are just saying, this is the standard deviation and this is the error, but this is just an estimation of the error, but we also know that our last digit is always uncertain in the measurement.
You mean some numerical error? Yeah, so I think you have to basically get a little bit out of the physics mindset and get into the statistics mindset, because the idea here is that our signal we explain, so we are not talking about numerical errors at all. So numerical errors are not addressed at all. So if that's your worry. The other thing is that what we're trying to do is we're trying to explain some observed data by a function of some input plus some stochastic term. And that's what we're trying to do. And
no, but I'm more thinking about the practical thing when I'm really doing the experiment now. Is this really enough just to estimate this error, or do I have to put the other error also into account?
No, I think you're referring to some kind of numerical errors in terms of the resolution of, so basically that you have a real value and you approximate this by some discrete number. I think that's what you have in mind.
In our matrix at the end there's a discrete number, right? In our matrix.
Yeah, sure.
We are gathering, and we don't know, like the next digit, what would this be?
Yeah, but this is so. I mean, one answer to this is that this is not of concern right now, because it's just not. It's not a part of the statistical theory, and it's not part of the actual data analytical procedures that you use.
I used it in my bachelor thesis actually, but I don't know. I used
Yeah, but what did you do then? So I think maybe we can discuss. So that sounds it sounds a little bit weird, the whole thing. So maybe we can send me an email about what you did, and then I maybe can give you an answer about what you did there. It's definitely not something that is of concern when talking about statistics and doing this. So in the sense that, not saying that this is not important, maybe it is important, but it's not what anybody else talks about.
Okay.
Good. So we are in the process of explaining data by means of some deterministic function, of course, in real space, which is then, of course, approximated by discrete values, like everything in when you use a computer, and some error. And we've now established that we can derive estimates for the true but unknown parameters. So remember that epsilon is distributed according to a multivariate normal distribution with the true but unknown variance parameter sigma square. And we've now derived our estimates for estimates for the subtleties. Please refer to statistics for data science. So we have these estimates now based on some data, and now the question is, first of all, what do we do with these estimates, and how do we get from these estimates to what we then see in brain imaging studies, where you see some blobs, and we are not talking about the question of why you see certain peaks and not other peaks. That's the question of random field theory based p-value correction and thresholding. So today we're talking about blobs in the sense of that these values that you see overlaid there are typically t-values, and then high t-values get brighter or hotter. I think that's really the name. Hotter values, and lower t-values get more reddish values. So these are t-values, so that's what I'm saying. So usually what you see in the results of brain mapping studies are t-values overlaid on some anatomical image. And the question is, where do these t-values come from, and what do they mean? And also, why do t-values have associated p-values, in the sense that these t-values have some distribution, and we can then assess how likely it is to see our observed t-value or some more extreme t-value under null hypothesis. So the question of the distribution will also come up today. And to get to that, we first should introduce the parameter estimate distributions. So that would be the distributions of the beta hat and the sigma square. And then we should define the t-statistic. So what that is and what it means. And then we should introduce the distribution of the t-statistic. Good. And this whole thing is, of course, strong frequentist statistics. So the the distributions, about the parameter estimates that we're talking about are frequentist distributions, not posterior distributions in the Bayesian sense, but frequentist distributions, which then also lead to the distribution of the t-statistic, which is of course also a frequentist distribution. And the first thing then to discuss is what this frequentist mindset actually means, and how this then results in our parameter estimate distributions. And that's, I think, so the first thing in a way is the most important thing, that you get into that, and sometimes people are a little bit confused by that, but I think it's relatively straightforward. So let's hope we get that clear. So you should think again about what we have. We have the general linear model, where we have, of course, the design matrix as specified for fMRI as discussed, and we have the error, and we've seen that this is the same as saying that we have a probability density function for the data, which is centered on x beta, which is our expectation vector for the data, and a spherical covariance matrix. Thank you. Now the question is, how does this relate to or what about the distribution and the data? So there you really have to strongly dissociate the model and the real world. Because in the real world, for one voxel, you have observed, maybe I give it a little Y star here now, which are your gray level MR signal values of this voxel over TRs. Yeah? So you have observed that, you have it stored on your computer, and these are, for example, values like this. And one last one. So it's an n-dimensional vector. Yeah. So this is what you have observed. This is what you have stored on your computer. This is what the experiment gave you. And the model, on the other hand, is saying a little bit more. The model says that you can potentially, or you can theoretically, let's say like this, you can theoretically sample data vectors from this multivariate normal distribution as long as you want, because it's just saying there is a distribution over data vectors. So let's write some realizations now like this. So this is just saying there are data vector realizations y1, y2, y3, which are distributed according to a normal distribution with true but unknown parameter beta and true but unknown parameter sigma square. And importantly, these yi for I, you can do that indefinitely if you want. These are the important point I didn't put there. So these are vectors, yeah. So these are not individual single values, but these are vectors, and our I here goes 1, 2, and so on. Yeah. So if you think about implementing this in a computer, you would use a multivariate Gaussian random number generator, set some beta value, set some beta parameter value, set some variance parameter value, have a design matrix, and then draw random realizations from this distribution. In the real world, you don't draw any, or you draw, the conceptual thing is that you also draw a realization, but only one. Yeah. So in the real world, you always have only one observation. In the model, you say, okay, I have a distribution over data points, so potentially I could sample many data vectors. Yeah, is that clear? So you really have to, the main thing to appreciate is that your observed data is one of the infinitely many realizations you could draw from the model. Yeah. Now, if you have, if you are on the side of the model, you can now, of course, think that if you have the first realization you can draw from the model, or use this, you can, of course, compute a better parameter estimate based on this first realization. Yeah? Now you again draw a sample from the GLM, and you use this sample to compute again a better parameter estimate realization. And let's do this one more. And again, you could go on with that. And then you have better parameter estimates, hypothetical better parameter estimates, that also have some probability to occur, because of course they depend on the random realization of y, and depending on the characteristics of y, certain better estimator realizations are more likely than others. And the question is now, what is the distribution of these better head estimates? Yeah, so that's one thing that we want to answer. Is that clear why you have this distribution? I mean, you don't have it in reality. Maybe also to establish that. In reality, what you have is one better head estimate, which is given by your design matrix multiplied with your real observed data. Yeah? So you have one value for your better parameter estimate. However, the model says we have a distribution, so we can potentially sample from that, because the data have some variability if we always apply the same function, namely the better estimator formula, so this xtx minus 1 xt to the data, then we also get observations of our better head parameter, and the question is, what is the distribution of them? And then, not too surprisingly, the same thing applies to the variance parameters. So if we use our first data and our first better estimate, then we get our first variance parameter. And of course we can also do this for the second one, and I will not write this all up now. And for the third one, based on the third realization. And again, the question is, if we then have these variance parameter, I think I'm forgetting a square here, variance parameter estimates, what is the distribution of these variance parameter estimates? And again, in real life, you only have one variance parameter estimate given by your actual observed data, your actual better parameter estimate, and that's all you have. Yeah, so that's the very important frequentist logic to that. You, in theory, well, the theory you impose on your data is that you say this is one of the many possible realizations I could have from my model, for which I don't know the true but unknown parameters, and I will never know, but I can estimate them, and I can now basically use the distributions that result from the data distribution for the beta parameters and for the variance parameter estimates, for the beta parameter estimates and for the variance parameter estimates to compare my observed beta parameter estimate and my observed variance parameter estimate. And the nice thing about the theory of the GLM is that these distributions here, so the distribution of the beta parameter estimates and the distribution of the variance parameter estimates, they can be calculated based on the distribution of the data, because of course that's where they're coming from, analytically, and then they can also be put together in the t-statistic, and again the distribution of the t-statistic can be computed analytically, and then we can compare observed t-values to this analytically evaluated t-distribution. But first we want to talk about now the distribution of the beta hat, of the beta parameter estimates and of the variance parameter estimates. Yeah, so far so clear? Good. Then the first question is now, if we have this logic and we have this distribution of data and we have beta hat defined as xtx minus 1 xty, what is a probability density over beta hat? And maybe put here beta distribution, beta hat, beta estimator distribution. And yeah, we will not go into the full theory behind that, but at least a little bit. So the thing is, the data is multivariate normal distributed, and normal distributions are mathematically nice to work with, and one particular thing that is known and has been proven for normal distributions is that if you linearly transform a vector that follows a multivariate normal distribution or multivariate Gaussian distribution, then the resulting vector is also multivariate normal distributed, and you can evaluate its expectation and variance parameter based on the original parameters and the linear transformation. So what I'm referring to here is the linear transformation theorem for Gaussian distribution. Which is a mathematical result, and of course, like with all mathematical results, it follows from some definitions, but how it follows, that's then a question of proving that this follows, and we will not prove this, but we will use the result. So what is the result? The result is if we have a random vector x, which is distributed according to a multivariate normal distribution with expectation parameter mu x and variance covariance parameter sigma x. So x here is supposed to be a random vector, so it's n-dimensional. Hence mu x is also n-dimensional, and sigma x is n times n. And we define another random vector y by multiplying some matrix with this, where A, it's easiest if it's n by n, but we can also make it m by n. It needs to be of full column rank, but that's a subtlety here. If we define y to be the multiple of, maybe I make small letters, then it's more in line with what we are using currently. If we define y like that, then this result states the following, namely y is also distributed according to a multivariate Gaussian, and it has expectation parameter mu y, where mu y is given by A times the original expectation parameter, and this would be then m times 1, and sigma y is given by A times the original covariance matrix parameter times AT, and this would be then m times m. Yeah, so the point here is that you know the original distribution, you know the matrix that carries out the linear transformation. Then two results follow. First of all, the resulting thing is also normally distributed, and you can directly evaluate the parameters of this normally distributed resulting vector using the original parameters, namely mu x and sigma x, and the linear transformation. Yeah? And this, of course, one would have to prove. It's a little bit reminiscent, of course, that if you multiply some random variable, and especially Gaussian random variables, by some constant A, then you scale the expectation parameter and you get the square variance of that, which you see here with this A twice. So this linear Gaussian transformation theorem, you find that under the Gaussian stuff in the lecture script. It's not proven. It's actually not hard to prove if you looked at the statistics for data science, where we discuss random variable transformation in much more depth. Then you see that this is fairly straightforward to show this linear transformation theory. Yeah. Any questions about this linear transformation theory?
Just about the dimensions. What dimension is A? Is it m times n?
Yeah.
Or, okay, so y is at the end it's dimension of m.
Yeah.
Okay.
Yeah. But of course, it can be that n equals n, but for the application that we have in mind, of course, it's actually n is smaller than n, because the application we have in mind here is, of course, this. And any other questions about the linear transformation theory? I mean, it's just a mathematical result that we use here. And if you are interested in why this holds, you would have to study the proof. That's essentially the point here. Now, of course, our beta hat is defined as xt x minus 1 xt times y. So here you just need to be a little bit flexible. So if you look at the linear transformation theorem, then what is called x there is here called y. It's of course a little bit confusing. And our A is here this xtx to the power of minus 1 xt, and our y is beta hat. Yeah. So that's if you want you want to apply this now to the case that we're interested in. What's this? So basically, we already can say something about our about the distribution of the beta parameter estimates, namely that it's normally distributed. It has a multivariate Gaussian, and of course here it's p-dimensional because our beta parameters were always p-dimensional, and it has an expectation vector mu beta hat and a covariance matrix parameter sigma beta hat. And then the last thing to do is essentially to evaluate what the parameters of this are, and this of course one can straightforwardly do. So first, if we look at mu beta hat, that should be the matrix R times the expectation of the original vector. So the matrix R is our xt minus 1 xt. And what was our original expectation vector? So what's the expectation of y? So it helps to look here. So here it says we should use the expectation vector of the original random vector that we are transforming. And now the original random vector that we're transforming is our y, our our data. So that's our y. And what is the expectation parameter of y? If you look at this here. Exactly. So that would be our mu x here. And then we see that we have xtx to the power of minus 1 times xtx. So what does that give us? So what does this xtx to the power of minus 1, or the inverse of xtx times xtx give? Yeah. So that would be the identity. We can briefly think about what identity that would be. So x is n times p, so the transpose is p times n times n times p. So xtx is a p times p matrix, and then we have two p times p matrices multiplied by one another, giving the p-dimensional identity matrix, which of course it has to be also because beta is p times 1 dimensional, and hence we get beta. So what does that mean? Well, beta is our true but unknown parameter value. And that means that the distribution of our beta parameter estimates has as expectation the true but unknown parameter value. Yeah? So if you sample many times and average over data slash beta parameter estimate realizations, you recover the true but unknown parameter value. Yeah? This is also referred to as that the beta parameter estimates is unbiased. So that's one thing. So that's our mu beta. The other thing that we also have to evaluate is our sigma beta hat. And for this we need our xt x minus 1 xt times the original covariance matrix. What is our original covariance matrix of the y in the GLM? this delta? No, sigma.
Sigma times that.
Yo. So this is what we put here. And then we need the transpose of this. So this is our A, sigma x, AT. Yeah, so this is what we are doing right now. Yeah, everyone happy? We have a scalar in here, so the scalar we can take to the front, and then we have xt x minus 1 xt, and then we have the identity in, and if you have matrices A, B transpose, what do you get? Because we have now a matrix product and we need to transpose the whole thing. So what is AB transpose? So that's the basic math stuff that is in the math preliminaries where you find this. So we have to xt transpose. So we have x, and then we have xt power minus 1 transpose. Our in, of course, doesn't do anything, so we can get rid of that straight away. And then again we see that we here have xtx to the power of minus 1 times xt, so we can get rid of that as well. And then I think we need, oh, there's a typo in the script because there's a weird t. Then we assume that we know, because I mean we would have to show it, but this is what I'm telling you, that the transpose of this is the same as this, which follows from the symmetry, because you have a matrix multiplied with itself, so it's a symmetric matrix. Then you have the inverse, also symmetric, and then you have the transpose of that, and it's then the same thing. So this is, you can get from basic matrix properties. It's not immediately clear, so this is why I'm basically introducing this on the fly, and we end up with this. Yeah. So now we have found that our probability density for our beta parameter estimate is the normal distribution, with expectation parameter being the true but unknown value, and covariance matrix parameter depending on two things, and that's actually important. So the covariance of the beta estimate depend on the error variance. So if you have higher variance for the error, then you have higher variance, or variance for the beta parameter estimate, and it depends on the design. So by because based on the design matrix, so by changing your design, meaning changing your design matrix, you can do things that make the variance of your parameter estimates smaller. This is also in the script, and we think we will discuss that in much detail this term. But it's one way to optimize or have at least have a kind of a target function or objective function for optimizing designs. Yeah, so that's the beta hat distribution. So it's Gaussian, it's m-dimensional Gaussian. Expectation parameter vector corresponds to the true but unknown beta parameter vector, and covariance matrix parameter is given by both the true but unknown variance of the data / the errors, and the multiplied by the inverse of the product of the design matrix. Good, so that was a little bit in detail. What we will not do in detail at all is the distribution of the variance parameter estimate, because essentially the mathematical machinery we would need to establish that is more not complicated, but it's just bigger. We would establish a lot more, so we focus on the result. And I think before the break, I mainly give you the result, and then after the break we look at a little bit at pictures, and then use this to motivate also the t distribution. So the basic thing is, so the basic question is, what is the distribution of the variance parameter estimate? And the answer is, it's a chi-squared distribution. However, the whole thing is not quite that simple. So it turns out that it's actually not the distribution of the variance parameter estimate that is chi-squared distributed, but a scaled version of it. So if you multiply the variance parameter estimate by n minus p and divide by the true but unknown variance, then this entity here has a chi-squared distribution with n minus p degrees of freedom. So in general, so what is a chi-squared distribution? Because maybe this is the first time you really see a chi-squared distribution. A chi-squared distribution is the distribution of the square of a standard normally distributed random variable. So if you have z, and that z is standard normally distributed, so you have univariate z that is distributed according to a standard normal distribution. So you have something like this, centered on 0. And now you look at the distribution of z squared, and then this is distributed according to a chi-squared distribution with 1 degree of freedom. Now, if you have multiple of such zi, and you sum them and square them, then these are distributed according to a chi-square distribution of n degrees of freedom. So that's the basic machinery of or the basic definition essentially of a chi-square distribution. So what you should intuitively have in mind here is, if you have a z that is distributed like this, so according to a standard normal distribution, then of course z can take on positive and negative values. But if you now square z, of course the negative values get, if you apply z squared, everything that you have in terms of negative values also becomes positive. So you cannot just have again a normal distribution, because a normal distribution is always symmetric and always also assigns positive probability density to negative numbers. So you need, what will happen is you get a different distribution, and how this distribution looks for one is actually relatively, or that's quite clear. So you basically have the things that are close to 0. If you square them, they will be, so everything here, they will be positive, and you have high probability density for those. This is 0. You have a 0 probability density for everything that is negative, and then as you go to larger values of z square, you get less probability density. If you now have multiple of those z variables, so if you're in this case here, then the chi-square distribution starts to look a little bit different. So I can show you an image. So this is here the chi-square distribution for n degrees of freedom. You can ignore this. This is just the CDF. And here we have n1, 2, 3. And you see what I've just shown you was for one z variable. And if you have 2, then you get a little bit more mass probability density allocated to larger values, and then at one point you get these peaks. So for 3 you get these peaks that are not on 0 anymore. Yeah, so these are chi-square distributions, and now the point here is that this variance parameter, which of course also results from a squaring operation. So if you think about this again, you have y minus x beta hat t y minus x beta. You have something normally distributed here and something also normally distributed here. You put them together, and then intuitively you again get something normally distributed, and then you square it. Yeah, so you have this thing here being normally distributed, and then you multiply it with itself, so you square it. So it's intuitively sensible that you get something chi-square distributed. To really show that, that would now require quite some writing down equations, and in the end what comes out is that the scaled version of the variance parameter estimate is chi-square distributed, so it's not that rewarding to do the whole derivation. Yeah, so the important thing is that the variance parameter estimate is not normally distributed. It can't be, because there's the squaring operation in there, and then it has the typical distribution for things that are normally distributed and then squared, which is a chi-square distribution. This chi-square distribution, however, depends on the true but unknown parameter value, and this will later then go away when we talk about t-statistics. Good. So appreciate that we did this to very different levels of mathematical depth. So the beta estimator distribution will be derived based on some result. The variance parameter distribution, I'm just telling you. Yeah. But of course, feel free to look more into this. It comes up always in classical statistics, and it's just basically deriving, this whole thing is about deriving the probability density functions of the results of transforming random variables, and that's what a lot of statistics is about. Good, so then after the break I think I will show you 2 pictures about this, and then we go into t-statistics. Then let's have a break and start again at 9, if there are no questions. No.